So we're looking at an exam question that certainly starts, when it starts, is about reaction of aqueous ions. But this question also goes on to be very clearly about transition metals as well. And you often get questions that feature both of those things. So in many respects, reactions of aqueous ions is an extension of transition metals, but I think it's kept separate in the exam specification, really because it also, the reaction of aqueous ions also features aluminium, which isn't a transition metal. So I think that's essentially why it's kept separate, but in many respects, it is an extension of the transition metals topic. So we've got here sort of a reaction. We focus on what's at the center of our reaction scheme. We've got this Fe3 plus hexa aqua ion. And one of the things to sort of notice about that is the fact that it is a 3 plus charge. And in the AQA specification, those metal hexa aqua ions with a 3 plus charge are considerably more acidic than those with a 2 plus charge. So I'm just going to write acidic here. So it would have a pH of maybe around 3. Now you'll notice that with reaction 1, it's with sodium carbonate, and sodium carbonate is a reagent that you use when testing for carboxylic acids. So one of the things is that, and carboxylic acids have a pH of around 3, and you know that you've got a carboxylic acid if you see fizzing. So, and that whole reaction is a neutralization reaction, and it's going to be exactly the same here. So we're going to get, it's a sort of a neutralization reaction. We then get a product that's a precipitate. Now, in the sort of reactions of aqueous ions, the majority of the precipitates, well, the precipitates are all in the reactions of aqueous ions, they all have no overall charge. So if we're talking about a complex ion, what happens is we get to the point where the complex ion has no overall charge, and that then results in it being a precipitate because it can no longer remain dissolved in solution or in water. So that's just something to sort of remember and bear in mind. If we look at reaction 3, and we're looking at what the change is, the only change is the charge on the complex ion, and therefore the charge on the metal, on the Fe ion, because that's the only thing that's can be changing charge here. So what we've actually got in this instance, if we look at reaction 3, is this is a reduction reaction. So all that's happening is then reaction 4, we have a reaction with concentrated ammonia, and we get another precipitate. Now, there is only one metal in the have a ligand substitution with ammonia, and that's when we use excess ammonia, and that's with copper. So with copper, if we use excess ammonia, then we do get some ligand substitution or ligand exchange, but that's not the case with any of the other metal ions that you have to know in AQA. So what we've got here is we've actually essentially got another acid-base reaction, and we're producing a complex ion with no overall charge. So we'll look at that shortly anyway. Then reaction 2, concentrated HCl. So really, concentrated HCl is here. This is a ligand substitution or ligand exchange reaction. Now with the reason Cl minus, because that's what we would have here, is interesting, or what you have to sort of pay attention to, is that if you do get ligand substitution, then what you would find is you would get a change in shape of the complex ion. So when we look at the hexa aqua ion, and I'm saying hexa aqua because it's 6 water molecules, or 6 water ligands, that would have an octahedral shape. But if we've got Cl minus ligands, then they're much larger. Each Cl minus ion is much larger than a water molecule. You can't fit 6 around. You can't have an octahedral shape. It's not energetically favorable, and so what we actually get in our ligand substitution here is we get change to a tetrahedral structure. So tetrahedral really features in the AQA spec when you've got Cl- ions when we're talking about complex ions for transition metals. Okay, so we've just sort of established ourselves, so sort of set ourselves up here, ready for the actual questions. So it asks us to give the formula of precipitate J and state its color. So it's a neutralization reaction. And it's a neutralization reaction that has resulted in a precipitate, and the precipitate will have no overall charge. So we've gone from 3 plus to an overall charge of 0 in precipitate J. So thinking about that, if this is an acid base, then the metal hexa-aqua ion is acting as a proton donor, is releasing H plus ions. And if it's gone from 3 plus to 0, it must release 3 H plus ions. These H plus ions will be coming off the water ligands. So for every H plus that is released, we are left with an OH minus in the metal complex ion. And if we've released 3 H plus ions, then we must have 3 OH minus ions. So our formula here is going to be FeOH3, and then we've got to still have 3 water ligands. That will also be 3. Now, I've not put square brackets around this formula because really those square brackets are to do with showing that something is an ion and has an overall charge. In the mark scheme, it does have a square bracket, so I guess you can put square brackets, but I don't think that's really correct. So then we come to the colour, and I'm afraid the colours of these various complex ions in the reactions of aqueous ions topic, I'm afraid you just have to learn them. There's no way around this. It is recall. I mean, you can argue some of these formulae that we're doing is a recall as well, but it helps if you understand perhaps with the formulae what's going on. But in case of the colours, I'm afraid there is no way around it, and you would just need to know that this was brown. Okay, so now we've got our equation, and again, it might just be something that you've learned off by heart, but I think, like I say, it always helps to know, to have a strategy in case you're perhaps doubting yourself. And we said that this is an acid-base reaction. We're reacting it with a carbonate, and if we think back even to our GCSE, if we did an acid plus metal carbonate or acid plus carbonate, then what we got was carbon dioxide and water, and we also know that we've got the precipitate here. So we know that we're starting with our metal hexa-aqua ion. And we know that we're reacting it with sodium carbonate. Now, in these reaction equations, they want the ionic equation. And with the sodium carbonate, that's an ionic compound. It's aqueous, so that means it's dissolved, which means that those ions are actually separate from each other. So the sodium ions are going to be acting as spectator ions here. So I'm just going to focus on putting in the formulae to begin with. I'm not going to balance it until the very end. We've already established the formula of J. So if we didn't get that right, that is going to make this final mark tricky. It's a sort of a consequential mark, I suppose, or consequence mark. We know that we get carbon dioxide, and we know that we get water. So how about balancing it? I think the best strategy to use here is to actually focus on the charges. If we've got 2 charged species on the left, but if we look on the right, no matter how many of the precipitate J's we have, or the carbon dioxides we have, or the water molecules that we have, we're still going to have an overall charge of 0, no matter what molar ratios we put in front. However, we can change the charge on the left. Now, when we're balancing equations, it isn't simply just about balancing the numbers of each element. It's also about balancing charge. So we must have the same overall charge on both sides of the equation. We have 0 on the right, and it's always going to be 0. But we can do things to change the left, and we need to make the left overall 0. And what we can focus on is we've got a 3 plus and we've got a 2 minus, and we've got to get those to cancel out. So the easiest way to do that is going to be to times the 3 plus by 2 and times the 2 minus by 3. So we will end up with 6 plus and 6 minus, and then they will cancel out to get 0. So I'm going to put a 2 in front of the metal hexaion, a 3 in front of the carbonate ion, and then it's now a straightforward way of balancing the rest of the equation. If I've got 2 of the metal hexaions, I've got to have 2 of precipitate J. If I've got 3 carbonates, I've got to have 3 carbon dioxides. And then if I just do a quick tally of what's left over, well, I'm taking 1 oxygen from each of the carbonates, so that it results in carbon dioxide, and I'm taking 3 hydrogens from each of the metal hexaions, so I am going to have 3 water molecules at the end. So I think charge is a really useful way sometimes of balancing equations such as this. So if we move on, it's then asking us to give the formula of L. So just to remind you which one L was. L was the complex ion that's being produced through a reaction of HCl, concentrated HCl. Notice this is testing your sort of, I guess, your appreciation that a complex ion with chloride ions is going to be tetrahedral. So that means you have to remember that formula. So it's going to be FeCl4, because that's our tetrahedral structure. The Fe ion won't have changed charge, so that would have been 3 plus. Each of the chloride ions are 1 minus, so we end up with a 1 minus charge overall. This also explains why it's not a precipitate, because we do have a charged metal complex ion, so it will dissolve much better in water. And then the equation itself, again, we're focusing on an ionic equation. We're starting with our metal hexaqua ion. Oops, sorry, just make sure I've got the 6 of those. 3 plus. Reacting it with chloride ions, well, you know, I can tell now it's going to be 4. I mean, I already know from the formula. This is just a ligand substitution. I'm making L. And then I'm going to get 6 water molecules. So one thing to just maybe mention in this is the fact that there would be an increase in entropy. We've got 5 on the left, and we've got 7 on the right. Doesn't automatically mean that it's a spontaneous reaction. It is possible that the enthalpy change is endothermic, but and therefore we don't know for sure that delta G is negative. I guess if the question implied it was, then you would assume, then you would go with that. 4.3. Now 4.3 is a tricky question and could blindside you probably quite considerably. One thing to say in general is that in exam questions, if they start with the word suggest, they are quite often the trickiest, and they're only ever worth 1 mark. So, you know, if you get a suggest question and you're completely stumped by it, please just move on and come back to it at the end, and don't stress about it. But it says suggest a reagent for reaction 3. So suggest normally means that you're having to really extend your application powers. So it's not necessarily something that's directly in the course, but they believe that you have the knowledge, if you've done the course, to be able to answer this question. So there's a bit of an extrapolation, I guess, of ideas. So let's just remind ourselves about what reaction 3 was. So reaction 3 is the reduction reaction. We're going from the 3 plus to the 2 plus. So what we're looking for is a reducing agent. Now, they have 2 possibilities in the mark scheme. They have one main one. And I guess this is about recognizing, I guess, patterns, and also thinking about other parts of the course. So one area where you probably have done a noticeable amount of, where you notice that you were reducing the oxidation state of a metal quite considerably, was with vanadium, going from +5 to +2, and you would have used zinc to do that. Also, when you've had various electropotential charts and they ask you for the most powerful reducing agent, almost certainly, I don't want to say it always is, but almost certainly it's ended up being zinc. And I think this is just one where you've got to make a sort of an educated sort of guess or an educated judgment here. And so the answer that they've got as the main answer is zinc. Zinc is a powerful reducing agent. It will reduce any of the other transition metals. If you think about the reactivity series you learned at the GCSE, zinc was just below carbon. It was like the first metal that wasn't, or the highest metal that wasn't group 1, 2, or 3. If we really want to make sure that it fully, and this is a general point as well, if we really want to make sure that all of the Fe3 plus is reduced to Fe2 plus, then we would really need it in excess. That's not an essential feature, but I think it's something that you need to sort of appreciate in general. If you want to make sure that something happens, you've got to ensure that the other reactant is in excess. So I guess anything that we can learn from this question, other than this is simply the answer to this question, is I think that zinc is a good go-to when it comes to when you need a powerful reducing agent. And if you are given an electropotential and zinc is on there, don't automatically assume that zinc is the most powerful one, but have a look and see if it sort of makes sense. Okay. Now we've got to give the formula of precipitate M. So we'll have to just go back and see what M was again, remind ourselves. So M is where we have gone from, so we've got to be a little bit careful here. We're going from the metal hexa aqua ion that's got a 2+ charge to precipitate. Now the principles behind this precipitate are the same as the principle behind precipitate J. So this is hydrolysis, or this is a acid-base reaction in this case. So we've got to have an overall charge of 0. We will be removing H's from the metal hexa aqua ion, but we've only got a 2+ charge, so we are only removing 2. So we end up with 2 hydroxides and 4 waters. Again, I'm not putting the square brackets around, but if you wish to, I think you're not going to get penalized, but it's not an ion, so it shouldn't really have them. And again, it's another one where you just got to remember the colours, and you've got to remember it's different to the Fe3 plus complex precipitate or solution. So this one is green. So now we move to a 6-mark question. So this is very clearly now about transition metals. So it says transition metal complexes have different shapes and many show isomerism. Describe the different shapes of complexes and show how they lead to different types of isomerism. Use examples of complexes of cobalt-2 and platinum-2. You should draw the structures of the examples chosen. So let's think about this. It's just said isomerism. Now, isomerism breaks down initially into 2 types, structural and stereo, and which then in turn break down further. And if we're thinking about just that first step, about what type of isomerism do we think it's going to be? Is it going to be structural? Is it going to be stereo? Is it going to be both? Then structural, which features chain, functional group, and position, that is not relevant to transition metals. So we're going to be talking here about stereo isomerism. Okay, so that's about different arrangements in space. And they're talking about shapes, so shapes clearly matter when it comes to stereoisomers. Shapes of complexes and show how they lead to different types of isomerism. So we've established it's stereoisomerism, and now they're telling us it's different types of isomerism. So this is about the different types of stereoisomers. So we have 2. We have geometric, and what we're really talking about here is cis-trans. So in the case of metal complex ions, we're talking about cis-trans, but we can also get the other one, which is optical. Okay, so we can get geometric and optical isomerism. Okay, and then it's asking us to use examples of cobalt-2 and platinum-2 to illustrate that. So why have they chosen those 2? Cobalt, that's an interesting one because cobalt is specifically not on the specification. However, I guess we've got to make a certain assumption that it's going to be fairly generic. And really, when it comes to shapes, the dominant shape is octahedral, and then it's a question of remembering the exceptions to that. So I think we can be very confident this is about an octahedral shapes. And then platinum is one of those exceptions. So you have done a specific platinum complex, which is in another part of the course, cisplatin. And the point about platinum is that it forms square planar. So we have two different shapes here that we can use to illustrate our different types of stereoisomerism. Now they haven't told us stereoisomerism yet, so we've got a feature that's got a feature in our answer. So we're going to start our answer with stereoisomerism. Is possible, and then it can happen certainly in these two shapes that we've established in octahedral and square planar complexes. Okay. Now we could now draw a square planar octahedral shape, but actually, as I'm going to use both of those to illustrate the different types of isomerism, I don't think that's absolutely necessary. So let's start with cis-trans. So there is a reliance that you need to remember that these types of stereoisomerism feature in transition metal complexes, or can feature. So cis-trans isomerism can occur in either, or both, I guess, but whatever, either square planar or octahedral complexes. And now we need to draw examples of this, and we need to show what we mean. So we'll start with square planar, and I'm going to use the cisplatin structure because why not? I mean, you don't have to, but given that that's a ready-made one in many respects, and the fact that you should know, its basic structure. So I always think it's best to draw the shape first and then to add the ligands onto it. So we have got Cl, H3N, H3N. Now platinum would be a 2+ charge. In fact, actually they mentioned this at the top, didn't they? Platinum 2. The chloride ions are 1-. There is no square brackets around this shape. There is no overall charge. It would have an overall charge of 0. This is our cis structure. So cis means on the side of. So we've got the ammonias on the same side as each other. We've got the chlorides on the same side as each other. Then if we want to draw the trans version, again, just draw the square planar shape. And now I've got to make sure that the chloride ligands are across from each other and that the ammonia ligands are across from each other. Okay. Again, obviously it's still the same complex. So there's no overall charge. Great. Now we've got to do the octahedral. Now the octahedral, it can be a little bit trickier about being absolutely sure that you are doing that you're actually doing a cis or a trans shape. So let's just draw the octahedral structure first. So we've said it. We've got told it's cobalt. I'm just going to draw the shape. what I'm going to do is, just to save myself a little bit of time in a second, I'm just going to copy that. So I've got it twice, because I'm going to have to do both the cis and the trans. Now, you've got to have something, a structure in which there is 2 of one ligand and 4 of another. That's how you're going to show the cis and trans. So let's assume it's one of those sort of precipitate structures, where we've got the OH instead of H2O. So we need 2 OHs. And what I'll do is I'll make the left-hand one the cis like it was with the square planar one above. Now, the way to determine whether you've drawn something that's cis or not is to look at the bond angle that between your 2 ligands. So if I put OH here and OH here, and I looked at the bond angle, that would be 180 degrees. If I put OH here and OH here, then I would have a bond angle of 90 degrees. And if I did it here and here, I would also have a bond angle of 90 degrees. And that's what's going to tell you that you've got cis, the bond angle, right? So that's your sort of method for checking. So to have a cis structure, you've got to have a bond angle of 90 degrees in this instance. It's also the same, actually. Cis was 90 degrees in our square planar as well. But we just didn't, it wasn't necessary to really think about the bond angle there. So going to have our OH and our OH. I think it's always useful to draw the ligands that are the important ones first. Get them in their place. So there's our nice 90 degrees. I'm going to do the trans one as well. It's got to be 180 degrees, so I'm going to have them across from each other. And now it's just a question of fitting in the water ligands. And one thing to say is always make sure that the oxygen is the end of, well, it's the oxygen that's at the end of a bond. I'm not going to draw a square brackets around this either, because this is also taken there's 2 hydroxide ions. It's cobalt 2. Yeah, so it's cobalt 2. So we've got no overall charge again. And then I'll just finish the ligands on the one on the right. So we've got cis shapes and we have got trans shapes. So we've dealt with the cis-trans isomerism. So now we've got to go on to the optical. So I'm going to change the page there. Now, optical isomerism can occur in octahedral shapes. Or octahedral complexes. And it only really occurs, again, focusing on your specification. I don't want to say this is universal truth, but as far as AQA is concerned, it exists when there are bidentate ligands. So that means a ligand with that can form 2 coordinate bonds. So it can exist when there are bidentate ligands. Now, you are expected to know 2 of bidentate ligands, and so if you are expected to know them, you should say what they are. So the 2 that you are expected to know are ethane dioate ions, which you can just write as a formula like this. Obviously, when it comes to the structure, you've got to do something different. And the other one is 1,2-diaminoethane. So we only have to choose one of those to draw. I'm going to do the diaminoethane. So hopefully I've still got my octahedral shape, just to save us a little bit of time. Now, I think the best way of approaching this is in the case of ethane diorate, at the end of each coordinate bond is an oxygen. In the case of 1,2-diaminoethane, at the end of each coordinate bond is a nitrogen. I think it helps to just draw those, what's at the end of each coordinate bond. So it would help if I've probably made these shapes a little too small actually for what I'm going to try and do, but I'm just going to try and put the NH2 parts of the molecule not perfect. Okay, so I've just done that. Do you know what, actually, I'm going to rub out this. This is just about me saving a little bit of time in my explanation, and I'm going to put that, I'm going to copy what I've got there. Oops, didn't need to do that. I'm going to copy what I've got there, put it on the right-hand side. All right, so now one of the things is these are bitendate ligands, which means that two of those H2Ns are like part of one single molecule. So I think you can get away with doing skeletal formulae here. So let's just do that again. That's the first carbon, that's the second carbon, and then we're back to the nitrogen. Okay, so we've made an attachment there. That's the first carbon, that's the second carbon, and that's back to the nitrogen. Which that should be a straight line. And then the last one, a little bit, not the best angle that I've done for myself here, but let's draw that one again. That's the first carbon. This is now the second carbon. Let's just do it a little bit longer, and then back to the nitrogen. Okay, and our diamino ethane does not have a charge, so we will have square brackets around this. The cobalt is still 2+, so you've still got to make sure that the whole shape structure is correct. Okay, right, now we're looking at the one on the right. We've got to do a mirror image. So it sometimes helps you, you don't have to do this, but it sometimes helps you to put like a dotted line, and you're thinking, I've got to have a mirror image. So we've got on the furthest away from the dotted line, we've got that. So that means I'm going to have to put it here to make sure it's a sort of mirror image. Okay. We have got this sort of at the top closest to the line, so that's going to be where the mirror image is going to be there. So this is where my drawings could have been a little bit better. In fact, I'm going to rub out that and put it on the other side to give myself a bit better space. And then we're left with the final one. And actually, tell you what, I probably should just rub out and swap that H2 and put it on the other side. This is not like essential, it's just to try and make, especially for you, look a little bit clearer, but also to show that you can flip these things around. And then I've just got to put my square brackets. And that is my 6-mark answer. I've demonstrated that stereoisomerism can feature in metal complex ions. I've done it with cobalt and platinum. I've got the two shapes, octahedral and square planar, and I've drawn examples of each. So I hope that was useful, and yeah.